So we will continue the tutorial and try to do part 2 of this problem. And so in this case, as you can see, we have to add the gradient part as well to get a better view of what's going on. So first of all, let's fix our gradient code, uncomment it, and then for each one of these temperature axis, we need a derivative. So we have a TZ derivative added, and so flux in z direction needs to be calculated as well using the same approach that we did earlier. And we won't have an image anymore and no quiver command, but we can add, because this is a three-dimensional field, we can add stream slices. So let's add a stream slice of our vector field, which is xyz, qx, qy, qz, and we need to add a stream slice at 10, 10, so on the right edge, on the back edge, and on the floor. But because it's a wall, we may want to come a little bit inside so that we can actually see the temperature streamlines along the floor and those two walls. And after this, we also want to make sure that the axis, it goes from 0 to Lx, 0 to Ly, and 0 to Lz. So that takes care of the stream slices. We will see those. Now we also would like to probably put some streamlines there, and to do that we need another axis here, SZ, and let's have streamlines. Maybe go from maybe at 2, 5, and 8, and same here, 2, 5, and 8. So these are 3 points along each axis, which total give us 3 times 3 times 3, 27 grid points from where the streamlines will start. If you don't remember this, look at the vector field tutorial again to make sure that you understand what am I doing here. And then we can add the stream slices or streamlines to that plot. We'll stick with the red color, and I think that does the job. Again, we need to make sure that the axis command is run on both sides. So let's take this axis command from here and copy it here as well. And here we should also put a color bar to see how is the temperature varying. To get an idea, and maybe at the top we can also compute the average temperature and put it at the top too. So right here we can say that T bar is equal to mean Tn, all the values. So, and we can display this mean temperature on top of the plot every time. So average temperature is equal to %.2f. So this one is showing all the value with all the decimal places. This will only show 2 decimal places, and we can put T bar as the first variable. So first variable gets displayed here, the second variable gets displayed here. Now we need to uncomment this subplot so that both the plots are showing on the plot. And we don't want this visualization to show at every time step. We may only want to show this every maybe say 5 minutes, because 5 hours is a long period of time. So in order to do that, what we can do here is start an if loop. So if mod of t comma instead of every second, let's display this every 10 minutes, so that's 600 seconds. So when mod t600, which means t is a multiple of 600, when it's equal to 0, that means t is a multiple of 600, only then go inside this block. And that way this will be only this code will only run when t is a multiple of 600. And if it's still very slow, you can change this. Turns out MATLAB takes longer time when it is doing displaying part than when it's doing computations. So this may help in a little bit better visualization and slowing down some of those visualizations that may take very long time. Now the other part that we need to add here is the sync. So far we have done all of the source part here, and in our case now we know that the source runs for 10 hours, and what we can do is here copy this code for the sync part maybe after the boundary, because the sync is on the boundary, and you can say that when the time is greater than 5 hours, that's when we want to start the sync part. And we can put sync somewhere here along one of the walls and set the temperature equal to 20, and that will basically form the sync. So it can be any of those walls. So let's pick one wall and then put a 4 pixel 9 to 11 9 to 11 as the little small set of pixels that serve as the sync. So that should do the job. Let's display this for maybe 3 iterations to get a, actually we have to run it at least for 600 iterations to see some visualization. So let's run it for 1200 iterations. So as you can see, it's overplotting because we missed clear the figure command, which should have appeared right here after the visualization starts. So clear the figure before you display anything. And I think we need to make sure that this 1200 is taking into consideration dt. So when I say dt is 10 seconds, that means every iteration here is 10 seconds. So keep that in mind. So if I'm saying run it for 60 iterations, that means run it for 600 seconds. So let's run it for 120 iterations, which will be 2 minutes. So as you can see, it ran 2 iterations in this case, 10 and so not 2 but 20, 10 minutes and 2 minutes. And looks like we may need to change the view a little bit. If we change the view maybe to 6518, you can see it at the bottom here. What am I reading? So maybe set minus 70 and 10. That may give us a better view of what's going on. So we'll change it to minus 70, 10 for both of the plots. And all you have to do is, after the plot has been completed, change the view to minus 70, 10. And we do this for both the plots. Now we can run this for a while to see what happens. So it's running, it's incrementing. It's supposed to increment every 10 minutes, so which is a good thing. It'll take us to 5 hours pretty fast. Now let's change this to so we want to run it for at least 15 hours. So 15 hours times 3600, and each iteration is 10 seconds, so that gives us 5,000 iterations. So we will run it for 5,500 iterations. And now I'm going to be quiet for a while because we will just see the iteration running. one point. Just keep an eye on the temperature as well. This is the average temperature and how it's rising over time. So after 5 hours, the vent has opened and all the energy is flowing towards the vent. And I think at 10 hours, which would be 600 minutes, the computer will stop. So all the flow is now going towards the vent. So you can see you can see how now this part is cooler and the whole of the room is hotter, and so everything is flowing towards the vent. And hopefully this gives you an idea how to run a 3D simulation of a PDE. And there'll be more PDEs that we'll be doing in next couple of labs, and hopefully that will clarify some of these things that we have been discussing in the class.